Hello, and today we're going to be looking at Unit 1 paper for CCEA Physics from 2021. So let's get started. So 2021 paper for AS Physics, that's the Forces, Energy and Electricity section. So they start us off with something very simple, state Ohm's law. So remember, Ohm's law relates to the relationship between current and voltage in the case of a conducting material, a metallic conductor. And so we say that the current through a metallic conductor is directly proportional to the voltage across it, provided the temperature is kept constant. So remember, Ohm's law, what's true and when it's true is if we keep the temperature constant. So again, this idea of what is true and when is that thing true, that's what your 2 marks are for. So part B then goes on to say, well, the 3 identical 40 ohm resistors are connected between 2 terminals A and B to form a resistor network. There are 4 possible ways the 3 identical resistors can be arranged to give the different values of resistance between A and B. In the boxes below, sketch the 4 possible arrangements. So obviously we could have the 3 of them in series, and we could have the 3 of them in parallel. And then there's 2 combinations with a series and parallel bit. Okay, so you could have one of the resistors in series with a parallel combination, and you could have one of the resistors in parallel with a series combination of 2 of them. And so we have a couple of other possibilities. So we have the idea of a series combination in parallel with one of the other ones, or we have a parallel combination in series with the other one. So this combo here is going to give us the highest resistance, this combo here is going to give us the lowest resistance, and these 2 are going to give us somewhere in between those 2 values. So they want us to calculate the maximum resistance that you can get between A and B, and that's obviously going to be what happens if you put them in series. And there's another calculation to calculate the minimum you can get, and the minimum we can get here is if we put the 2 of them in parallel. So we need to do a calculation for each of those. Well, in series it's very easy, that the resistance, the total resistance, is the sum of the values. So we put in our equation for 3 resistors in series, and then we fill in the values for those. And that gives us a resistance in the first one of 120 ohms. Now, when we put them in parallel, we're going to get a different equation. We get the more complicated version of the equation for when we put stuff in parallel, that 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. And filling that in gives us 1 over 40 plus 1 over 40 plus 1 over 40 equal to 1 over RT. And so we've got 3/40ths there equal to 1 over RT. And the fact that it's equal to 1 over RT means that RT itself is going to be that fraction upside down, so we get 40 over 3. So RT itself will equal 13.3 ohms. Question 2 part A asks us to define the term work done in a mechanical system. So remember, this is just stuff that's straight out of your notes. So we think about a force causing movement along the direction of the force. So work done is the product of the force and the distance moved along the direction of the force. Part B then says, in February 2013, a 20-meter wide asteroid entered the Earth's atmosphere above the town of Chelyabinsk in Russia. Sorry if I'm not pronouncing that correctly. Prior to entering the atmosphere, the asteroid had a mass of 1.25 times 10 to the 7 kilograms and was moving at a velocity of 1.9 times 10 to the 4 meters per second. Calculate the kinetic energy of the asteroid. Give your answer in terajoules. Okay, so we're looking for kinetic energy here. Very, very straightforward stuff. We're filling in our kinetic energy equation. So the kinetic energy of a moving object is a half times its mass times its velocity squared, half mv squared, and filling that in from the values they've given us, we can sub in now. And so we've got a half times the mass, which is 1.25 times 10 to the 7, times v squared, and v was 1.9 times 10 to the 4, and then we square that after putting it in. So we need to bump that through our calculator now. So I've put down the first 4 significant figures of my calculator value because we have input numbers of that 1.25 and that 1.90 that are only quoted to 3 significant figures. So we should only quote an answer to 3SF. So instead of calling it 2.25, that's 6 there in the 4th digit. The idea here that this one allows us to think about rounding this up. So we should quote that to 3 significant figures as 2.26 times 10 to the 15. So what would that be in terajoules then? So 2.26 times 10 to the 15. So mega is 10 to the 3. Giga is 10 to the 9. And tera is 10 to the 12. So you realize that gives us 2260 terajoules. So again, this rule about using your input numbers to guide how many significant figures you use in your output numbers is important. So 3 significant figures going in, 3 significant figures coming out. Part 2 then, friction with the atmosphere of the Earth caused a rapid deceleration of the asteroid. While travelling 60 kilometers through the atmosphere, the kinetic energy of the asteroid was reduced to 15% of its original value. Use your answer to part B1 to calculate a value for the average frictional force of the atmosphere on the asteroid over this distance. So this is like an idea that you've got this average force, it causes this slowing down over the period of, or over the distance, of 60 kilometers of motion. So the average force and that distance is taking us back to our definition of work, really, isn't it? So if we've got 15% of the kinetic energy left, we have lost 85% of the original kinetic energy. So we need to find 85% of the kinetic energy and put that equal to the work done, and that will allow us to figure out a force. So we start by stating what we're basically looking at here, and the idea is that the work done by the atmosphere, the force that the atmosphere creates, will equal this loss of kinetic energy. So the average force times that 60 kilometers will equal the loss of the energy of the asteroid. So the work done is going to be this force that we're looking for times 60 kilometers, which is 60 times 10 to the 3 meters. And we put that now equal to 0.85 of that original kinetic energy. So we have already calculated this value, 2.256 times 10 to the 15. And I'm just going to keep it in the 3 significant figures that they had for the previous answer in case that makes it diverge too much from the mark scheme. So we need to get f on its own and calculate a value now. So just bringing everything to one side, and then we just bump that again through our calculator. Sorry, I'm just noticing that I have 3 times 10 to the 3 where I should have 60 times 10 to the 3. Let me just correct that. And that gives us a value, after putting it through the calculator, of 3.2 times 10 to the 10 newtons. So a massive, massive force. And again, it's the average force because it wouldn't be constant. As the object slowed down, the force would change because the force of like an air resistance is velocity dependent. But it does give us a way of calculating the average force. Part 3 then, the asteroid exploded at a height of 30 kilometers above the town of Chelyabinsk. This produced an intense flash of light and a sound wave. Many people on the ground saw the flash of light and ran to look out of windows, and they were then injured by flying glass from broken windows caused by the sound wave coming. Calculate the time delay between the arrival of the light and the sound from the explosion, assuming that the sound was traveling at 340 meters per second. So we have a distance there in that 30 kilometers, and we have a speed here, so we should be able to calculate a time. So we do a distance over time calculation with those two numbers, and that gives us 88.2 seconds, but we'll just write it as 88. I'm sure people aren't going to be worrying about the 0.2 of a second. It's just the approximate time for a person perceiving the flash and how long it is roughly until the sound turns up. So 3A, again, we're given some more bookwork. Explain the difference between a scalar quantity and a vector quantity. So it says physical quantities may be classified as either scalar or vector. Explain the difference between a scalar quantity and a vector quantity. So remember, the scalars have a magnitude, and vector quantities have a magnitude and a direction. They include direction information. So it's the direction information that provides the difference. They both have some kind of size to them, scalars and vectors, but the direction is the unique property that vectors possess. We always represent them with an arrow showing which way they're pointing. So when you're ticking these boxes, you're thinking about which ones do I not represent, because they're saying, tick the ones that are scalars. So which ones do we not represent with an arrow? Well, force gets represented with an arrow, but mass doesn't. And so we can put mass down as being a scalar. Acceleration, we would show a direction on that, so it's not. But again, time is a scalar, temperature is a scalar, and distance, they don't say displacement, so it is distance. They would all be scalars. Part C then, a student makes the following statement. Both momentum and kinetic energy of an object are vector quantities as they both depend on velocity. Okay, explain why the statement is incorrect. So momentum of an object is m times v. That's fair enough, and v can have positive and negative values. If you think about a straight line, you can think of the positive values as having direction in one way up the road, and negative values having direction the other way up the road. However, when you get to kinetic energy, you square the velocity. And remember, what would happen then was that the +2 velocity, say, up the road, when it got squared would give you 4, and the -2 velocity down the road, when you square it, would also give you 4. So you couldn't tell which of those kinetic energies came from which velocity. So the squaring of the velocity makes it not really have a direction anymore. Hopefully that makes sense. So I'm just saying that squaring the velocity removes its direction property. Part D then, a boat of total weight 35,000 newtons is anchored in a harbour as shown in figure 3.1. To achieve equilibrium, the anchor exerts a force F sub A of 6,000 newtons at an angle of 25 degrees to the horizontal. This is needed because the water exerts a force Fu due to both upthrust and the current. Consider the boat to be a point mass of weight W, and a simplified diagram of the forces acting to achieve equilibrium is shown in figure 3.1b. Okay, so if you can imagine what's going on here is you've got a current flowing along this way, sort of trying to drag the boat in this direction, and the idea is that there's an upthrust added to that, giving you this sort of resultant, which is basically between the upthrust and the I suppose it's a frictional force that the current provides on the boat. The difference here is because the boat is static and the current is moving, the friction provides a force in the direction of the current. Okay, so we say that this force, Fu, hilarious, sits at an angle theta to the horizontal here. And so it will have components. So if you think about it, you've got a vertical component of this, a horizontal component of this, and this other force here has horizontal and vertical components. And so we basically resolve the vectors and write equations of the equilibrium. So there's, horizontal equilibrium, vertical equilibrium, and we write expressions for each thing and put them into equations. So there's vertical equilibrium. So Fu sine of theta would be its vertical component is equal to Fa sine of 25 added to the weight W. And we also have horizontal equilibrium, where Fu cos of theta equals Fa cos of 25, and there is no other, there's just those two components acting against each other. So if we call them equation 1 and equation 2, the standard way to solve this would be to divide equation 1 by equation 2, because Fu sine theta over Fu cos theta simplifies to sine theta over cos theta, which is tan theta. And then we have to also divide the right hand sides. So you end up with that expression that tan theta equals Fa sine 25 plus W over Fa cos 25. And so theta is the inverse tan of that filled in. So we need to bump that through the calculator in order to get our theta. And that gives you like 81.7568, etc. degrees, so which we'll call that 82 degrees. Now we need to put that back through one of the equations in order to get our answer for Fu. Put it back through the cos equal to cos one, probably the easiest. Again, if we put that through the calculator, we should get a value for Fu. So if you use those values, you get 39072, which doesn't quite agree with the mark scheme, but it'll obviously be depending on how much of the accuracy of this value that we rounded up here. So when you use some more of the accuracy of that, you get closer to the value. I think the mark scheme says 38,000, but we're going to obviously get 39,000 for that. So I'll assume that the markers have been clued into that and will know to adjust according to what value you've used there. Question 4 then. In the sport of baseball, a home run is scored if the batter hits the baseball with enough force to enable it to clear the perimeter of the playing area without bouncing. Treating air resistance on the ball as negligible, the motion of the ball can be considered to be that of a projectile. What is the name given to the shape of curve path that the ball follows through the air? Okay, so again, this is basic bookwork. We're meant to remember that the shape is parabola, that it's parabolic. And as far as the description is concerned, remember the description of a projectile motion is that you have two sort of independent motions perpendicular to each other. You have one direction where there is only constant speed, and a perpendicular direction where there is constant acceleration. So you're describing two perpendicular motions with very specific properties. One that has only a uniform velocity and one that has a uniform acceleration, constant acceleration. So it says the ball leaves the bat with an initial velocity u at an angle of 45 degrees relative to the horizontal as shown in figure 4.1. On the axes, figure 4.2, sketch a graph to show how the horizontal velocity varies from the moment of impact with the bat t equals 0 to the time when it clears the perimeter of the playing area t equal to t. Label this line h. On the same axis, sketch a graph to show how the vertical velocity varies from the moment of impact t equal 0 to the time that it clears the perimeter of the playing area t equal to t. Label this line v now. What they don't tell us is that this t equal to t, they don't say specifically that this t equal to t is where it hits the ground outside the playing area. It says clears the perimeter, so you can imagine it's still in the air. So this won't be a symmetrical graph because it still hasn't landed by the time they're talking about here. But what we realize that it's a 45 degree thing. So the magnitudes of both the horizontal and the vertical velocity will start the same because they're both the cos and the sine of 45 degrees. So the sizes of the vectors will be the same, and therefore these two graphs are going to start from the same point. And the horizontal one, because of its behavior, remember that it's going to be the one that has a constant value. So we're going to have one graph that's a constant value, one graph that starts in the upward direction. So if we say, take for example upward to be positive, this second graph is going to be constantly decelerating, so you're going to get a slope on this thing. At some point it's going to cross the axis here and head negative, but not necessarily from a value to a value because it isn't hitting the ground. It would be from a value to an identical value if it was hitting the ground at t, but they've explained that this is just where it leaves the perimeter. So it's going to be from a value to maybe some lesser value, but it won't have hit the ground yet because they haven't explained that it's hit the ground. So the value of the horizontal motion will remain constant. So you try and draw the best horizontal line. I've struggled to draw it horizontally on the iPad here. Obviously you can get a ruler out and draw it horizontally all the way up to t, because the horizontal motion doesn't change in a projectile. The vertical motion does, however, but it has a constant acceleration of the value of g. Therefore there's a slope on this second graph that is steady, and it'll go through 0 if we assume it has reached the apex of its motion before it crosses t. It will actually go through 0 and start to go negative by the time it gets to t. So the important thing is that the two vectors will have the same magnitude, so they start at the same point. And that's because the horizontal and vertical components of this vector are going to be the same magnitude as each other because it's 45 degrees. And so we get a constant motion, so the horizontal velocity is constant. We get constant acceleration, so the gradient of the vertical velocity graph is constant. So we get two straight lines, one with a downward slope. (5a) State Newton's second law of motion in terms of momentum. So this is the idea that momentum is m times v, and that we can sort of represent the force, the resultant force, in terms of the change of momentum. So if you imagine that the impulse equals the change of momentum, like ft, then we can divide both sides of that equation by t to get the resultant force. So if you think in terms of what this is saying, this top line's change of momentum, this bottom line's how long it took. So this whole expression here is the rate of change of momentum. So we can say that the resultant force is equal to the rate of change of momentum, or proportional to the rate of change of momentum of the object. So something along those lines. Rate of change of momentum of an object is directly proportional to the resultant force acting. Or you could say equal to, seeing as how that's what we've got in that relationship there. Certainly here we have found that they're equal. So directly proportional is acceptable and equal is acceptable. Part B then, July 2019 marked the 50th anniversary of the Apollo 11 mission in which humans landed on the moon for the first time. The Saturn V rocket, shown in Figure 5.1, used in the Apollo program, remains the most powerful rocket ever built. Prior to liftoff, the mass of the Saturn V rocket was 2.77 times 10 to the 6 kilograms. The engines had to produce enough thrust to accelerate the rocket to 8568 kilometers per hour in 2.5 minutes. Show that 8568 kilometers per hour is equal to 2400 meters per second when quoted to 2SF. Okay, so this is one of these unit conversion things. 8568 kilometers can be written in meters, and an hour can be written in seconds. Okay, so we rewrite kilometers per hour in how many meters that is and how many seconds an hour is. So it's a distance over a time, but we want to write it in meters divided by seconds rather than in kilometers divided by hours. And so that is what we get. That's what they asked us to demonstrate. Part 2, calculate the magnitude of the thrust required assuming the mass remained constant throughout the 2.5 minutes. Okay, because in reality the mass would change as it burnt fuel, yeah? So we need to establish a set of parameters like the upward force, downward force, mass of the thing, and do an F equals ma calculation. So we've got a thrust acting upward and a weight acting downward, and the weight is related to the mass, so the weight is equal to mg. And so you should use the g from your formula sheet in these kind of questions. So 2.77 times 10 to the 6 kilograms times 9.81 will give us the value of W. So T minus W equals ma, just basic resultant force equal to ma, Newton's second law. But we need to get A from like a UVAST calculation based on what they told us about the motion. So we need to write out a UVAST list and solve it for A. So we know that it starts at U equal to 0. We know it reaches 2400 meters per second. We know it takes 2.5 minutes to do that, so the T will be 2.5 60s, which is 150 seconds. We don't know the displacement, and we don't know A because we're trying to find it. But we do have everything we need now, because A would be V minus U over T. So A is going to be like 2400 over 150. So A equals 16 meters per second squared. And now we take that into our Newton's second law. So we've got T minus W equals ma. So T will equal ma plus W. And we know the weight value. And we can multiply the mass value by 16. So we should be able to get T. So if we put that through our calculator, we should get a value for T. So it pops out of your calculator like that. Like I added the 16 and the 9.81, so I multiplied 2.77 times 10 to the 6 by 25.81. Because you can think of that as ma plus mg, so it's m times a plus g. Now that doesn't exactly agree with the mark scheme, but that'll be down to where you round it up. The mark scheme says 7.11 times 10 to the 7, but it'll be just a rounding issue. So part 2, says that this engines of Saturn V only had an efficiency of 12%. Calculate the magnitude of the theoretical maximum thrust produced by the engines. So what we're saying is that this value we've got is 12% of the maximum thrust. So what's the maximum thrust? Well, we just write that as an equation. So the value we've got is 0.12 of Tmax. So Tmax is going to be, if we divide both sides by 0.12. So put that through your calculator, and you get 5.96 times 10 to the 8 newtons. So, in reality, both the mass and the weight of the rocket would change throughout the 2.5 minutes. Discuss whether you think these quantities would increase or decrease. Okay, so if you think about it, you're using up fuel. So if you use up fuel, the mass of the object will reduce. Therefore, the weight of the object will reduce. So automatically, because of the change in mass, the weight of the object will reduce. But you're also getting further away from the Earth. And so the effect of gravity will also decrease just because you got further away from the Earth. So there's two reasons why your mass will decrease because of the loss of fuel, but your weight will decrease because of the loss of fuel and because you're getting further away from the Earth. So something that explains both changes, those are your two reasons. So we've got a decrease in mass because you're using up fuel. That'll cause W to decrease. And then you've got a decrease in the strength of gravity as you get further and further away from the planet. Okay, so I'm going to stop there and I'll cover questions 6 until the end in a second part of this video. See you later, and thanks for watching.